So Jupiter, Saturn, and Uranus were big planets that were known, and the calculations were made as to how slightly different than the perfect ellipses of Kepler the planets ought to be going, Jupiter, Saturn, and Uranus, by the pull of one on each other. And when they were finished, the calculations, and the observations, it was noticed that Jupiter and Saturn went according to the calculations, but that Uranus was doing something funny. Another opportunity for Newton's laws to be found wanting, but courage. Two men, both who made these calculations, Adams and Leverrier, independently and at almost exactly the same time, proposed that the motions of Uranus were due to an unseen as yet new planet. And they wrote letters to their respective observatories telling them to look. Turn your telescope and look there and you'll find a planet. How absurd, said one of the observatories, that some guy sitting with pieces of paper and pencils can tell us where we'd look to find something new planet. And the other observatory was more, the administration was different. And they found the Neptune. More recently, in the beginning of the 20th century, it became apparent that the motion of the planet Mercury was not exactly right. And this caused a lot of trouble and had no explanation until a modification of Newton's. This did show ultimately that Newton's laws were slightly off and that they had to be modified. I will not discuss the modification in detail. It was made by Einstein. Now the question is, how far does this law extend? Does it extend outside the solar system? And so I show on the first slide evidence that the law of gravitation is on a wider scale than just the solar system. Here is a series of 3 pictures of a so-called double star. There's a third star, fortunately, in the picture, so you can see that they're really turning around and that nobody just simply turned the frames of the pictures around, which is easy to do on astronomical pictures. But the stars are actually going around. And by watching these things and plotting the orbit, you see the orbit that they make on the next slide. It's evident that they're attracting each other and that they're going around in an ellipse. According to the way expected, these are a succession of pictures going for all these different periods of time. I think, yes, it goes around this way. And they didn't see it well when it was too close, and here it is in 1905. My slide is very old. It's gone around maybe once more since. And you'll be happy except when you notice, if you have noticed already, that the center is not in a focus of the ellipse, but it's quite a bit off. So something's the matter with the law. No. God hasn't presented us with this orbit face on. It's tilted at a funny angle. And if you take an ellipse and mark its focus and then hold the paper at an odd angle and look at it in projection, the focus doesn't have to be at the focus of the projected image. So it's because its orbit is tilted in space that it looks that way. It looks like it's not the right pattern. But it's all right, and you can figure everything out satisfactorily for that. How about a bigger distance? There's forces between the stars. Does it go any further than these distances which are not more than 2 or 3 times the solar system's diameter? Here's something in the next slide that's 100,000 times as big as the solar system in diameter. And this is a large number of stars, tremendous number of stars. This white spot is not a solid white spot. It's just because of the failure of our instruments to resolve it. But are very, very tiny dots, just like the other stars, well separated from one another, not hitting each other, each one falling through and back and forth through this great globular cluster. It's one of the most beautiful things in the sky, as good as sea waves and sunsets. And the distribution of this material, it's perfectly clear that the thing that holds this together is the gravitational attraction of the stars for each other. And the distribution of the material in the sense of how the stars peter out as you go out in distance permits one to find out roughly what the law is of force between the stars, and of course it comes out right that it is roughly the inverse square. The accuracy of these calculations and measurements is not anywhere near as careful as in the solar system. Onward, as gravity extends still further. This is a little pinpoint inside of a big galaxy, and the next slide shows a typical galaxy. And it's clear that this thing again is held together somehow, and the only candidate that's reasonable is gravitation. But when we get to this size, we haven't any way any longer to check the inverse square law. But there seems to be no doubt that these great agglomerations of stars and so, these galaxies, which are